For a long time, the first billion years of cosmic history were, well, they were mostly just a concept. Our view was so limited that the earliest stages of galaxy formation were basically a locked room. We had plenty of theories, of course, but actually seeing what was happening back then was incredibly difficult. And this brings us right to the core mystery that a new era of astronomy is finally starting to tackle. How did everything we see today, the first stars, the first galaxies, even the first supermassive black holes, form so incredibly fast? Where did all the basic building blocks, things like heavy elements and dust, even come from in such a short amount of time? So in this explainer, we're going to dive into the recent breakthroughs that are giving us the first real answers. We'll start with the tools that are making it all possible, then explore two huge findings about early galaxies and their black holes. And finally, we'll talk about what this really means for the future of cosmology. To unlock that once inaccessible era of cosmic history, you, of course, need the right keys. And the new insights we're about to cover are really only possible because of the way two very specific observatories are now working together. All right, so here are our two main players, the James Webb Space Telescope, or JWST, observing from space, and the Atacama Large Millimeter/Submillimeter Array, ALMA, which is this incredible network of radio telescopes down in Chile. Now, on their own, they are incredibly powerful. But when you use them together, they give us a view of the early universe that is, and I'm not exaggerating, completely revolutionizing the field. So what's the magic in this combination? Well, it's that they see fundamentally different things. A really good way to think about it is to imagine a galaxy is like a city. JWST is fantastic at seeing the hot, energetic stuff, the bright stars and glowing gas. That's like looking at a city's lights from above at night. ALMA, on the other hand, is tuned to see the cold, raw materials, the huge reservoirs of interstellar gas and dust that actually fuels star formation. That's like seeing the city's hidden infrastructure, its plumbing and its power grid. This chart shows you exactly why this works. Over on the left, in the blue and green, that's the part of the electromagnetic spectrum that JWST sees, ultraviolet, visible, and near-infrared light. That's where we see stars. Then, way over on the right, in gray, that's ALMA's territory, the far infrared and millimeter wavelengths. This is where cold dust and gas give off their very faint glow. So, to really get a complete picture of a galaxy, its stars, its fuel for new stars, and all its dust, you absolutely need both. Okay, so now that we've met the tools, let's get into what they've actually found. And the first big surprise is about the galaxies themselves. The picture that's emerging is of a universe that got very complex very fast. One of the first major discoveries from ALMA was finding huge amounts of dust in galaxies when the universe was only 600 million years old. I mean, that was really unexpected. See, dust is made of heavy elements, which have to be forged inside stars and then released when those stars die. Finding so much of it so early on was a genuine puzzle. And the implication of that is pretty profound. The whole process of star formation, of enriching the universe with chemicals, and of making dust, it all must have been way faster and more efficient than our theories had predicted. The first galaxies, it turns out, weren't just these primitive blobs of stars. They were already sophisticated chemical factories. Let's look at a specific example that just shows the power of this tag team approach perfectly. This is a galaxy called Crystal 08. First up, here's what the Hubble Space Telescope saw. And as you can see, it looks pretty clumpy and irregular, which is kind of what you'd expect for a young, chaotic galaxy. Now let's switch to JWST's view of that same galaxy. Its powerful infrared vision cuts through a lot of the haze and gives us a much more detailed map of the stars. But, it still looks pretty clumpy. If we stopped right here, our conclusion would be that this is just a messy, disorganized system. But this is the crucial next step. This is what ALMA sees when it maps out the cold gas. And what it shows is a completely different story. Underneath that chaotic, clumpy mess of stars is a smooth, orderly, rotating disk of gas. This suggests that stable, disk-like structures might have been in place much, much earlier in the universe than we thought, just hidden from view. Okay. So the second major finding from this new partnership moves from the galaxy as a whole to the powerful engines churning away at their very centers, supermassive black holes. And here, the results are just as significant. A really central question in galaxy evolution is about the relationship between a galaxy and its black hole. Here in our local universe, we see a pretty tight connection. Bigger galaxies tend to have bigger black holes. But the big question is, does that relationship hold true all the way back at the dawn of time? This plot shows us what JWST has been finding. Let me just walk you through it. The vertical axis is the ratio of the black hole's mass to the galaxy's total star mass. The horizontal axis is just the star mass. Now, that dense gray cloud, that's the established relationship we see in the local universe today. But look at those colored dots. Those are the new discoveries from the early universe. They are way off, sitting far, far above the local trend. These early black holes appear to be shockingly massive for their galaxies, some of them containing up to 10% of their galaxy's entire stellar mass. Now, it's absolutely essential to bring in some scientific nuance here. As exciting as this is, the researchers themselves are very careful to point out a few caveats. First, measuring the total mass of the stars in the galaxy is really tricky, especially when the super bright light from the black hole can just wash everything out. Second, the methods used to estimate the black hole masses also have their own built-in uncertainties. And third, we could be running into what's called a selection effect, meaning we're just more likely to find the biggest and brightest black holes first. These are really critical things to keep in mind as this field continues to develop. So what do we do with all these revolutionary yet still very preliminary findings? Well, it's really important to put them in the right context. We're not looking at final answers here. We're looking at the very first detailed sketches on a completely new map of cosmic history. As the authors of the paper this explainer is based on conclude, the combination of these two observatories is, frankly, nothing short of revolutionary. For the very first time, we can actually take detailed measurements of the gas, the dust, and the stars in the universe's first galaxies and see how they're all arranged. These mature galaxies and these overmassive black holes, they aren't the end of an investigation. They are the start of brand new ones. Why was dust production so efficient? How in the world did black holes get so big, so fast? Did the black holes come first and then the galaxies grew around them? Or did they grow together in some way we just don't understand yet? These are the big questions now. The very first findings from the combined power of JWST and ALMA have already challenged some of our longest-held models of how galaxies and black holes form. It really just reinforces the core of the scientific process. New data lets us sharpen our theories and ask even better questions. As we continue to fill in this new map of the cosmic dawn, our understanding of where we all came from is going to keep evolving.